In section 10.2, we are going to look at how to now simplify radical expressions. So first of all, I want to start with a nice fact, and that being if I have the square root of two numbers being multiplied together, I can actually distribute the square root so that I have the square root of 4 times the square root of 3. I can split the inside of the radical up, and so that it only applies to each individual term. And so in this case, the square root of 4 would be 2, and so I can simplify this now down to these 2 times the square root of 3. So that's our nice fact that we can take factors or split up a radical inside and then apply the square root to both terms. So we're going to use that to help us simplify radical expressions. So our first example is to simplify the square root of 80. Now what we're looking for here is perfect square numbers. And remember, perfect squares are like 1 squared which equals 1, 2 squared equals 4, 3 squared equals 9, and so on. So 9, 16, 25, 36. We're looking for those numbers. And what we're going to try to do is actually factor 80, the term inside a radical, to see if any of these perfect squares are factors of it. If they are, then we can simplify it, just like we did in our nice fact where the square root of 4 is equal to 2. So if we have one of these numbers, we can then simplify it by taking the square root of that number. So 80, if I break this down, is going to be 4 times 20. And actually, I can break 20 down to 4 times 4 times 5. Again, that's the square root. If you'll notice, 4 times 4 is 16. So this is the same thing as the square root of 16 times 5. And now I can use my nice fact. So the square root of 16 times the square root of 5. I'm just applying my square root to both terms individually. Now I can simplify the square root of 16. Remember, 16 is 4 squared. So the square root of 16 is simply 4 times the square root of 5. Let's try one more example. I'll leave the other one up there. Square root of 54. Now 54 is the same thing as 4 times 14. Or you can think of 8 times 7. But I want the 4 here because that's our perfect square. 8 times 7 doesn't help us because 8 and 7 are not perfect squares. I'm looking for those perfect squares as factors. So again, I have the square root of 4 times 14. I can split this up using our nice fact. I have the square root of 4 times the square root of 14. And now I can simplify my square root of 4 to 2 root 14. Second thing I want to look at is how do we multiply radical expressions. Again, there is a nice fact. We're actually going to go the opposite direction. If I have the square root of 4 times the square root of 3, that's equal to the square root of 4 times 3. In fact, we're going the opposite direction. The first nice fact, we took it and distributed our square root to both terms. Now we're going to undistribute it or combine them back together. Here's why this is helpful. Let's say I have something like the square root of 2 times the square root of 14. Neither one of 2 or 14 are perfect squares, and neither one of them have perfect squares as factors. So we can't actually simplify them in their current state. However, if we multiply them together, this becomes the square root of 2 times 14, which would be the square root of 28. And 28 as a factors would be 4 times 7. 4 again, perfect square. I'll apply my first nice fact. So the square root of 4 times the square root of 7. Square root of 4 is 2. So I'm left with 2 root 7. Let's try one more. In this case, however, if you'll notice, we have numbers outside of our radicals. So what we're going to do is simply multiply our, I'll say, like terms. We're going to multiply our outside terms first, And then we'll multiply our radical terms just like we did in the last example. So my first step, we're going to multiply 4 and 5. And then I'll multiply the square root of 2 times the square root of 8. 4 times 5 is 20. And 2 times 8 is 16. Conveniently, the square root of 16 would just be 4, so I'm left with 20 times 4, simplifying square root of 16. And 20 times 4 is 80. The last thing I want to look at is how to simplify expressions that would include variables. We're going to do a very, very similar state, except this time we do have an extra few steps. So step 1 would be to do the prime factorization, break all the numbers up, break all the variables up, find how many pairs we have, how many perfect squares we have that we can take out. Step 2 then would be to remove those pairs. And lastly, if we take a variable out and it's a odd power, so either x to the first power, x to the third power, or the fifth power, we have to use an absolute value. I'll explain that when we get there. So let's look at the square root of 90 times x to the third times y to the fourth times z to the fifth. First thing, nice fact, we can split all these up and apply the radical to each term. So I'll have the square root of 90 times the square root of x to the third times the square root of y to the fourth times the square root of z to the fifth. Next, I'll break each one of these up, trying again to look for those perfect squares. 90 is 9 times 10. X to the third, again, a perfect square would be any number that's squared. And so x squared would be a perfect square. And so I can bring this up as x squared times x. And then y to the fourth is y squared times y squared. And then z to the fifth would be z squared times z squared times z. Now I can go ahead and remove my pairs, my perfect squares. Square root of 9 would be 3, so I'm left with 3 root 10. Here I have an x squared and an x. Again, just like I had 9 is the same as 3 squared, I moved out to 1, 3. I'm going to take the x squared and move it outside my radical, so I'm left with just x. And then I have 1x left over. I have 2 y squareds, so each one of those can come out to become just a y. So I'm left with y times y, or y squared. And lastly, I have 2 z squareds and a z. So I'm left with z squared in front and a z left over behind. The next step I'll do is actually combine things to look a little nicer. I'll take all the terms in front of the radicals, put those in front of a radical, and all the terms left from the radical, I'll recombine into one larger radical. So I'll take the 3, the x, the y squared, and the z squared in front, and I'm left with a 10 x z. So I've done step 1, I did step 2, and now I'm looking at step 3. Step 3 says I need to put an absolute value on any odd power variables. So looking at this, I have a 3, which is not a variable, an x to the first power, which is a variable and odd. Y squared and z squared are both to the second power, which are even. So I have to put an absolute value around x. Now, why do I have to put an absolute value around x? Here's the reason why. Let's give this situation. I will say I have a variable, x, which is equal to negative 3. And I want to know what the square root of x squared is. So the square root of x squared, I'll apply my first one, I'll substitute in for x. That's the square root of negative 3 squared, which is 9. And the square root of 9 is 3. Notice that this is a positive number, and that actually anytime we take the square root of a number, it has to be positive. So we looked at last section, if I had a negative number under the square root, it ends up being an imaginary number. We're not dealing with those right now. So every time I take the square root of a number, it's a positive number under the radical, it'll be a positive number outside the radical. So if we took the square root of x squared, without knowing what the value is, we would say this is just x. But notice, our original x was -3. But if we actually put -3 in for x, our result down here is 3. And so we need to somehow account for that. We need to show that once we've squared it and then taken the square root, it's going to end up being positive. And how we do that is by applying the absolute value. So therefore, we're saying that the square root of x squared is equal to the absolute value of x, which the absolute value of -3 is indeed 3, so that does check out.